Welcome back everyone to Aviatrix Deep Dive with Saad. In this session, I'll be discussing AWS FireNet. As a reminder, you need to watch the previous FireNet session, which is a prerequisite for all the CSP-specific FireNet session, where I discussed all the basics of the FireNet, including the common features across all the clouds. So let's now dive deep into the FireNet in AWS. There are two transit FireNet gateways in different availability zones for resiliency. Let's draw it out. This is a transit FireNet VPC. Let's say its CIDR is 10.0.0.0/23. There are two availability zones, and we are going to draw two Aviatrix gateways per availability zone. So this becomes your transit FireNet, which is a primary gateway, and this is your transit HA gateway. Let's say the first one is AZA, and this guy becomes AZB. These gateways are connected with each other using a GRE tunnel. The minimum size of these transit FireNet gateways is C5 extra large or C5N extra large. So extra large or C5N extra large. We recommend you to use the Nitro series for performance reasons. For transit FireNet gateways, the minimum number of interfaces required are 4. So you have to have the EC2 instance that can provide you 4 network interfaces. Now let's talk about these 4 network interfaces. If I'm going to draw, this becomes my transit primary, and let's say this is transit HA, has 4 interfaces. Let's say this is ETH0. This becomes ETH1. This is ETH2, and this is ETH3. E0 is the interface where controller is communicating with the gateway. So you want to make sure the security group that is managed by the Aviatrix controller is allowing the port 443 access here. So basically this security group, I'm just letting you know that port 443 is open in the inbound direction for the access from the controller. In this security group, we also allow the transit VPC CIDR, so the transit CIDR, to basically go anywhere. And why we need that? Because when we have a connectivity to on-prem, and then your firewall management is, let's say, sitting in the on-prem world, it wants to manage the firewalls. Let's say the firewalls are here too. Wants to manage the firewalls using the private IPs. Then let's say the connection is something like this. You do have Aviatrix edge devices, and here you are going to have tunnels to the transit. Now, when you wanted to manage, and let's say right here is your firewall management station. When this guy wants to manage the firewalls, it gets to the transit using the Aviatrix tunnels. And then from here, we are going to utilize the Aviatrix Transit Gateway ETH0 interface. traffic gets back here, now traffic is going to hop back onto the ETH0 interface. And since these firewalls are going to be in this CIDR space, that is the reason why when you take a look at the security group on ETH0, you will see the entire transit FireNet CIDR space allowed to speak to anything outside. All right, now let's go back to ETH1. So ETH1 is the interface which is unused. So for AWS deployment, we don't use ETH1 interface at all. All right, now let's talk about the ETH2 interface. ETH2 interface is the interface on which transit FireNet gateways are communicating with the firewalls. All right. And we also have a security group which is open for quad zero, like all the traffic. And the reason is because your application could have RFC 1918 prefixes, or your application could be using the IP address in non-RFC 1918 because some applications might be using the public IPs. In order to accommodate everything, we are going to have the quad zero open for everything. Now ETH3. So ETH3, as you can see, is the communication between the transit primary and transit HA gateway. So it becomes the E3 on the HA side too. And again, as I mentioned previously, this is a GRE tunnel between these two gateways to communicate with each other. Yes, there is time when we are going to communicate over this GRE tunnel, and I'm going to explain in the next few minutes. So which basically means we are going to again see a security group on both of our gateways in the inbound direction, and then the security group has a rule, pretty much the same rule as the ETH2, which means we are going to open it for the quad zero because the application could have the RFC 1918 or non-RFC 1918 IPs. So from the deployment perspective, you need to create the Transit FireNet VPC from the Aviatrix controller. When you create the Transit FireNet VPC, what basically happens at this point? You went onto the controller, create a VPC, make sure you click on the transit one. Now it is going to create the Transit FireNet for VPC for you. So actually what it's going to do, it's going to create, let's say you are going to create the gateways in two different availability zones. This becomes your AZA, and this becomes your AZB. What Aviatrix controller is going to do is going to create two subnets in each availability zone. The first subnet is going to be, I'm going to just write it down here, it's going to be gateway and firewall management subnet. Same thing in AZB, gateway and firewall management subnet. And we are going to create one more subnet in these availability zones, which are the firewall ingress and egress subnet. At this time, when we create the Transit FireNet VPC, by the way, this is a Transit FireNet VPC. We are also going to create a public route table. And all these four subnets are going to be associated to this particular route table. At the same time, we are going to create another route table, which is a private route table, but no subnets are going to be associated to this private routing table at this point. When you are going to deploy the gateways in this Transit FireNet, then what is going to happen? First of all, the controller is going to give you a choice whether you want to deploy in the standard mode or in the insane mode or high performance encryption. Let's talk about the high performance encryption first. When you are going to create the Aviatrix gateway, Transit FireNet gateway in insane mode, first you have to check the box that says insane mode. You check it. Once you check it, under the subnets, deployed subnets, it's going to now give you a different options, which is all /26. So we need /26 because insane mode, we are going to create a lot more tunnels than in the standard mode. So all you have to do at that point is to go back into the drop-down menu and select /26 per availability zone. At this point, we are going to create a third routing table, and that routing table is for your insane mode or HPE, for your primary gateway. Let's say this is the primary AGW, which is Aviatrix AGW. And this is again a route table. When you create the HA gateway in insane mode, exactly the same thing is going to happen at that point too. And we are going to create a third routing table for HA AGW. And the subnets, which we created like /26 subnets, will be associated to this routing table. Now what is going to happen when you are going to create the standard mode? In the standard mode, when you don't check the insane mode or high performance encryption box, at that point, the choices of the subnets are different. At that point, you are going to pick the subnet in the respective availability zone from the gateway firewall management options. So let's say you deployed the Aviatrix gateway. Let's say this is the transit gateway, which is the primary one, and you have also deployed the transit HA1. At this time, you wanted to make sure that these transit FireNet gateways have the transit FireNet function enabled. Right now, you can pass the traffic across from one VPC to another spoke VPC, which is the application VPC, but you cannot attach any firewall because the transit FireNet functionality is not enabled yet. So what you need to do, you need to go back to the Aviatrix controller and then select this transit FireNet gateway, and then enable the transit FireNet functionality. When you enable the transit FireNet functionality, at this time, two subnets will be created here again. So these subnets will be DMZ Exchange and DMZ Firewall subnets. And same thing is going to happen in the availability zone as well. So what is the purpose of these subnets first? So the purpose of this DMZ exchange is basically the subnet which Aviatrix controller is going to use whenever it's going to send the traffic from the primary Aviatrix transit gateway towards the HA gateway, or vice versa. So whenever this is a situation, we are going to use this DMZ exchange subnet. And when Aviatrix Transit FireNet gateways, when they need to communicate, they need to send the traffic over to the firewall, at that point, we are going to use this DMZ firewall subnet. Okay, so this is between the transit gateways, and this is between the transit and firewalls. Again, same thing is going to happen in the availability zone B as well. So a total of 4 subnets are going to be created. So respectively, we are going to create 4 routing tables too. DMZ exchange routing table, DMZ firewall routing table, DMZ exchange HA routing table, DMZ firewall, HA routing table, and associate all these 4 subnets accordingly. If we wanted to look into the routes, like what routes are going to be there for these routing tables that we just discussed. So first, let's talk about the DMZ firewall routing table. Once we start looking into this DMZ firewall routing table, then we will see a quad 0 route, and that will be pointing towards the Aviatrix gateway. Let's say this is the routing table for the primary guy. So it will be pointing towards the primary transit FireNet gateway, AGW, Aviatrix gateways, and ETH2 interface. So basically what we are saying firewall, whenever you need to send the traffic, your default gateway is ETH2 of your primary transit. And same thing is going to happen to the DMZ firewall routing table for the HA. Here we are going to say that whenever you need to communicate with the transit gateway, you need to just send the traffic over to the ETH2 of transit HA gateway. Okay, now what about the exchange routing table? So let's write that one down too. As I explained previously, the DMZ exchange is to communicate between the 2 transit gateways. So if I have the traffic, if I am the primary transit gateway, I want to send the traffic over to the HA, then what should I say? That if you need to communicate, then the quad 0 will point towards the E3 of HA gateway. So it becomes the ETH3 of HA gateway. And if you see the same routing table for HA gateway, it will point towards the primary gateway, just to make sure that we are sending the traffic to the right destination. Okay, I'm going to just erase this, and then when we come back, then we will talk about the different architectures. Let's take a look at this architecture. Here, I have drawn 2 parallel multi-cloud network architecture for region number 1. The reason could be there are a couple of business units. Let's say first one is for business unit 1, the second architecture is for business unit number 2, and they don't agree on certain firewall rules. At that point, what you can do, you can create a parallel architecture within the same region for those business units. They can control their firewall rules based on their requirements and application needs. So that's for region number 1. Now region number 2, or it could be your CSP number 2, have exactly the same architecture with the firewalls, and they can communicate through the Aviatrix transit connectivity like this. Now let's discuss another architecture where you wanted to make sure that one FireNet is dedicated for your east-west traffic, while the other FireNet is dedicated for your egress. Let's say if this is your requirement where the enterprise wants to have a separate east-west FireNet, and at the same time they wanted to have the separate egress where the traffic from the application destined for the internet is going to use entirely separate dedicated FireNet, then this is the architecture is going to look like. So basically the RFC 1918 will be towards this guy, RFC 1918, And the quad 0 will be destined towards the green links. And the blue links is for any RFC 1918 communication. Now, what you need to do in order to deploy this thing, you want to make sure when you deploy on the egress one, you need to disable the traffic inspection. And at the same time, you need to enable egress through the firewall from only this egress FireNet. So that way, the quad 0 will be propagated to all those inspected VPCs. So they will install the quad 0 coming from this egress transit FireNet, not the east-west. And for RFC 1918, since the inspection policy is configured on this one, then the traffic will be coming towards the east-west firewall. So this is called a dual FireNet in the scenarios when enterprise requires dedicated east-west and dedicated egress. Like always, you need to create the connection policy between the network domains and also the FireNet policies as well. If you have a dual transit FireNet architecture in both multi-region or multi-cloud environment as shown here, and you would also like to provide connectivity between them, then make sure you are connecting only east-west transits via transit connectivity and filter out the default routes accordingly. Now let's do a packet walk for a small transit FireNet architecture. I'm going to draw 2 spoke VPC and 1 transit VPC. All right, in this architecture, let's assume in VPC 1, application A wants to communicate with VPC 2, application B, through this transit FireNet. As a part of the Aviatrix control plane, the Aviatrix controller actually creates the RFC 1918 summary routes in all the VPCs and then points towards the Aviatrix gateways. So now when application A wants to communicate with application B, it sends the traffic over to the Aviatrix spoke gateways. So that becomes your step number 1. Now, Aviatrix spoke has 2 ways to get to the VPC2 because every spoke is going to have the 2 tunnels, one tunnel with the transit primary and then the second tunnel with the transit HA, even though I'm showing you only one connectivity right now. So in reality, what it's going to be something like this. And same thing with the VPCB as well. Again, I'm drawing only for the primary gateway here. So once the traffic gets to spoke primary in VPC number 1, it has 2 paths. Either sends the traffic over to transit primary or transit HA. Based on the hashing algorithm, let's say it picks the first transit right here. So at this time, when the transit receives the traffic, then it's going to check, okay, is there any FireNet policy configured for this? If the FireNet policy check is there, then the transit FireNet is going to redirect the traffic over to the firewalls. And now what firewall is going to do, firewall is going to inspect the traffic, and after inspecting the traffic, sends the traffic back over to the transit using the DMZ firewall subnet and routing table, because the default route points towards the transit primary gateway. Now, when the transit receives the traffic, it is destined for B. So it is going to send the traffic either to the spoke primary or spoke secondary. In this scenario, let's assume it is going to send the traffic over to the spoke primary. Now traffic gets to this guy. Traffic received, and now spoke knows exactly that this is the VPC CIDR, is the destination. then it's going to use the ETH0, send the traffic to B. Now, B application, when it returns the traffic, it could arrive on spoke A or primary or HA. Again, assume it comes back to spoke primary. At this time, instead of sending the traffic spoke primary, sending the traffic to the primary transit gateway, it sends the traffic, the hashing algorithm tells to send the traffic over to transit HA. Now traffic comes back over to the transit HA. Transit HA has the firewall, but this is not the correct firewall, because the firewall that initially received the first packet was the firewall that was attached to the transit primary. So at this point, what transit HA is going to do is going to use the DMZ exchange subnet and routing table, where it will see the quad 0 pointing towards the primary transit gateway ETH3 interface and sends the traffic over to this guy. This is going to be our step number 7. Once the traffic gets there, now transit gateway is going to send the traffic over to the firewall. And what firewall is going to do is going to inspect the traffic and sends the traffic back over to the transit gateway. Now, transit gateway is going to send the traffic either to this spoke, HA, or then the primary. Let's say the traffic comes back to the primary spoke, and then the primary spoke is going to send the traffic to its destination. That's how you are going to send the traffic from application A to application B across Aviatrix Transit, where FireNet is enabled for the traffic inspection. Packet walk of egress traffic inspection would be almost identical, except you need to turn on egress through firewall feature that will advertise quad 0 route to all the inspected application spokes. Traffic will follow this default route to get to the transit FireNet and then redirect it to the firewalls as usual, but this time after inspecting the traffic, firewall will NAT and use its egress interface to go to the internet by using transit FireNet public routing table, where quad 0 points to IGW. Now let's talk about the firewall health monitoring. There are two different mechanisms that Aviatrix controller utilizes. The first mechanism is the keep alive via firewall LAN interface. So this is the firewall LAN interface, and what Aviatrix controller is going to do is going to ping the firewall LAN interface from Aviatrix Transit Gateways ETH2 interface. So what basically it does, it improves the failure detection time and accuracy. And Aviatrix Transit Gateways sends these pings every 5 seconds with a timeout of 20 milliseconds. So anytime you are going to lose 2 consecutive ping, then Aviatrix controller is going to declare this firewall as dead. But ping will continue in the background just in case this firewall comes back up. Once the firewall comes back up, we will place this firewall back in the load balancing pool for you. This firewall is going to remain in down state once you deploy this firewall, because what you have to do, you have to go back in your firewall and then enable the policy which will allow the ICMP on this LAN interface from the Aviatrix controller IP. Otherwise, it won't let you do that. As an enhancement, what Aviatrix controller has done, just in case the ICMP are getting lost, something is going on over there, then as a backup mechanism, Aviatrix also allow, or as a follow-up, it allows the TCP keep alive too. So once the ICMP fails, then the detection is more robust using these TCP keep alives. The only thing which you need to do is to make sure that in your firewall policy, you are allowing the port number 443 from the Aviatrix Transit Gateways ETH2 IP addresses. So no configuration you have to do on the Aviatrix side. The configuration which is required, that will be only on the FireNet side. The second mechanism is using the management interface, not the LAN interface which we are using here. Let's talk about the load balancing and then the failover mechanism of the Aviatrix gateways and then the firewalls. So in this scenario, you can see if there are multiple firewalls. Right now I'm showing you one. Let's say if we have 2, 3, 8, 10 firewalls attached to the same transit, then all these firewalls will be attached to the same ETH2 interfaces, and they will be using the same DMZ subnets and then the routing tables. And Aviatrix Transit is going to take care of the load balancing and hashing of all these firewalls attached to the same transit gateway. By default, Aviatrix Transit FireNet provides the 5-tuple hashing, which basically means source IP, source port, destination IP, destination port, and then the protocol type. But for legacy application that can only work with the 2 tuples, Aviatrix also provides the flexibility of configuring either 5-tuple hashing or 2-tuple hashing. Let's say if there is some kind of a failure in the firewall gateway, let's say primary gateways goes down, then the detection time for the Aviatrix controller is about 7 to 10 seconds with fast timers turned on. And then only failed gateway firewalls are going to be removed. For example, if HA gateway goes down, then only the firewalls that are attached to the HA gateway, we are going to declare them as dead. And all the traffic is going to be merged only over to the primary gateway, and this firewall is responsible for all the traffic inspection. If only one of these firewall goes down, then Aviatrix Transit Gateway is going to remove that particular firewall only from its load balancing algorithm. Aviatrix also has integration with AWS Gateway Load Balancer. Let's take a look at the architecture. As you can see over here, these are the spoke VPCs, your application VPCs, and this one is your Transit FireNet VPC. Here, we do have Gateway Load Balancer endpoints after the Aviatrix Transit gateways, and then Gateway Load Balancer. Behind the Gateway Load Balancer, you have the firewalls, and then in order for you to get to, or application to get to the internet, then there is a NAT gateway. So the traffic flow is going to look something like this. When the traffic is destined for the internet, the spoke application sending the traffic to the Aviatrix Transit. Transit is going to send the traffic to the Gateway Load Balancer endpoint. The Gateway Load Balancer endpoint sends the traffic over to the Gateway Load Balancer. Then Gateway Load Balancer is going to hash the traffic to one of the firewalls, and the firewall is going to send the traffic to net before it gets to the internet. In this architecture, the high level of control is there. At the same time, high visibility is available. All the troubleshooting tools are available for you, the monitoring. So the design pattern number 2 is going to look something like this. The design 2 is the TGW orchestration that Aviatrix provides. Spoke 1 and Spoke 2, let's say they wanted to communicate with something on the internet, they send the traffic over to the TGW. In TGW, this is the TGW FireNet VPC. Traffic comes to the Aviatrix Transit, sends the traffic over to the Gateway Load Balancer endpoint. Gateway Load Balancer endpoint sends it to the Gateway Load Balancer, then to the firewalls, then to the NAT gateway, and then to the internet. Here you have limited visibility because you don't have the Aviatrix gateways in each application spokes. And same thing with the troubleshooting tools too. You will have troubleshooting tools, but not at the same extent as the design number 1. Now let's take a look at the design pattern number 3. So in this design pattern number 3, when you have this orchestrated TGW using the Aviatrix, but what if you wanted to remove the Aviatrix transit gateways from here? like design number 2 now becomes the design number 3 without the Aviatrix transit gateway. At this point, all the visibility, the control, the troubleshooting tools, everything is going to go away. At this point, you still have the access to the internet using the gateway load balancer endpoint, and this, in all these 3 designs, Aviatrix controller is going to orchestrate the gateway load balancer for you. At this point, I'm going to discuss the last architecture that Aviatrix supports for AWS, which is the orchestrated TGW. In this scenario, let's say if you have your application spoke VPCs, those are attached to the TGW, like TGW attachments. Then we have TGW FireNet. Here we have Aviatrix TGW FireNet gateways, or just a transit gateways, and those are attached to the firewalls. So this becomes your spoke 1, that becomes your spoke 2. This is iNet. In this architecture, Aviatrix Transit FireNet is going to be providing the east-west traffic inspection, also providing the egress traffic inspection, and north-south traffic inspection as well. For example, if you do have your on-prem and you have connected your on-prem to this architecture, then that traffic inspection is also provided by the Aviatrix Transit. All right, so that's all I have for AWS FireNet. In the next session, I'll be discussing Azure FireNet. Thank you very much for watching.